Am I audible?
Yes, ma'am.
So the day before yesterday, we have started with her 8th unit of lattices and Boolean algebra. In that, we have seen lattice as posets and definition, examples, and properties. Today, we will see the special lattices and all these Boolean algebra and its concepts related to Boolean algebra. Here we have seen lattice is a partially ordered set. The example given for that this is this one XYZ is the set inclusion, and power set of this XYZ set are given with this diagram. The diagram is known as hash diagram, and it is the best example of lattice. Okay. Then this is the lattice of integer divisors of 60. These are the numbers which get divided by 60, or sorry, which divide 60. Okay, and ordered by refines. The refine operation and given here like this: 1, 2, 3, 4. These are the individual items, and then they are grouped like this: one item, then two items, then one item, two items, then one item, then one item. This one means different combinations are there. Same is here. Again, the different combinations are here. Okay, means this we can see here. 1, 2, 3, 1, 2, 3 is gathered, and then again 4. 3 elements are there. How we can go to make this? Yes, first element is we can combine this 1, 4 together and 2, 3 as it is. Okay, and what the second is? Second refinery is here. We can 2, 3 is already there. So 1 we can combine with this 2, 3 and 4 as it is. Okay, we can do like this also. 1, 2, 3 is there, and here it is done. 1, 2, 3 is there, and 4 is there. We also can do like this: 2, 3, 4 is there, and 1 is there. It is 2, 3 is there, and 1 is there. Okay, each and every element is combined with the different combinations, and altogether it is going to form this one: 1, 2, 3, 4. It is the example of lattice. Again, this is lattice of positive integers ordered by less than. 1 is less than 2, 2 is less than 3. Again, 1, 2, 3 are less than 4. 1, 2, 3, 4 are less than 5. Like this, it is the one more example of lattice we have seen. Then this is the lattice of non-negative integer pairs. Non-negative integer pairs, this is given as a plane. Okay. Excuse me. Plane means what? The coordinate plane. X and Y coordinates are there, and according to that, non-negative is there, means only positive integers are given there. Okay. All the points are coordinate plane is also one type of lattice. Okay. This is about the examples of lattices. Then we saw the duality. We can take duality as AND operation is exchanged with OR operation, and OR operation is exchanged with AND operation. Similarly, union operation will be exchanged by intersection operation, and intersection operation will be interchanged by or exchanged by intersection. Means union and intersection, we can go for this also. and or we can go for that also. Then a lattice L is called a bounded lattice if it has the greatest element 1 and the least element 0. We know that a lattice is bounded lattice. Okay, means it is bounded means what? Lattice is what? It has one greatest lower value and it has least upper value. Okay, least upper bound is there and greatest lower bound is there. So if that least upper bound is 1 and greatest lower bound is 0, then that lattice will be known as bounded lattice. Okay, here power set example is given there. Then this one is properties of bounded lattice. What are those? This one, A or 1, it is giving 1. A and 1, it is giving A. A is any element that is from that lattice. And A or 0, it is giving as A, and A and 0, it is giving 0. Theorem, what the theorem is? Prove that every finite lattice L, A1, A2, A3, N is bounded. Okay. A1, A2, A3, N is the lattice. The greatest element of lattice we give by A1 or A2 or A3 or N. Okay. Also, least element we give by A1 intersection A2 intersection A3 intersection dot dot AN. Since the greatest and least elements exist for every finite lattice, hence L is bounded. Okay. We can give greatest elements by ORing all the elements and least elements by ANDing all the elements. Taking the intersection of elements, we can, or sets, we can give the least element, and taking the union of all the elements, or we can perform our operation in all the elements, we can get the greatest element. As we can calculate or evaluate these values or these elements, so we can say that L is bounded lattice. Then here it comes the concept of sublattices. This also we have seen, I think. Consider a non-empty subset L1 of a lattice L. Okay, then L1 is called a sublattice of L if L1 itself is a lattice. Okay, L1 should also be the lattice to be the sublattice of L. Itself is a lattice, that is the operation of L, that is A or B belongs to L1 and A and B belongs to L1, whenever A belongs to L1 and B belongs to L1. सेट आणि सबसेट माहिती आहेत आपल्याला, सेम त्यासारखी ही कॉन्सेप्ट आहे लॅटाईस आणि सब लॅटाईस. आपण खाली एक एक्झाम्पल घेतलंय D30 असे नंबर्स जे 30 ला डिवाइड करतात. कुठले आहेत तो सेट काय आहे? 1 2 3 5 6 10 15 30. ओके, लिस्ट एलिमेंट इज 1 and greater element is 30. So what we get is, yes, means for sublattices what we have to take is all the sublattices, 1 will be the least element and 30 will be the greatest element. The middle elements can be changed. Okay, so here we have taken all the combinations of that. 1 and 30 is constant. Sometimes we can take 2 3, sometimes we can take 2 5, sometimes 2 6, sometimes 2 10, and sometimes 2 15. Okay, then we can go for 3 5, 3 6, 3 10, and 3 15. Okay, then we can go for 5 6, 5 10, 5 15. Then 6 10, 6 15. And lastly, it will be the 10 15. Total, it will have 15 sublattices. Okay, from those we have taken here 7. Getting? the sublattices we can define here. Then it comes the isomorphic lattices. It is the new concept that is today we are going to see. Two lattices L1 and L2 are called isomorphic lattices if there is a bijection from L1 to L2, that is a function such that f of A and B is equal to f of A and f of B, and f of A or B is equal to f of A or f of B. What is there for isomorphic lattices? There is a function from L1 to L2 such that f of A and B is equal to f of A and f of B, and f of A or B is equal to f of A or f of B. If this is the case, if these two conditions are getting satisfied, then and then we can say that L1 and L2 are isomorphic lattices. Okay, how we can go for that, we will see with the help of example. Determine whether the lattices shown in figure are isomorphic. Okay, these two lattices are given here. We have to find that whether these are isomorphic or not. What the solution is, the lattices shown in figure are isomorphic. Consider the mapping F is from A to 1, B to 2, C to 3, and D to 4. Okay. Now what we are doing is, for example, f of B and C, okay, is equal to f of A, which is equal to 1. How it is? We'll see that f of B and C. What is f of B and C? Here, 2 and 3 is given. Okay, f of B, how the function mapping is there? B is mapped to 2 and C is mapped to 3. So here 2 and 3. How those are given? 2 and 3 means B and C. Okay, 2 points are here. F of B is 2 and f of C is 3. Both connect to the point A. Yes or no? This B is connected to A, C is also connected to A. So this 3 is also connected to 1 and this 2 is also connected to 1. So what we can say that these two lattices are isomorphic. Okay, means we can function to the corresponding elements A to 1, B to 2, C to 3, and D to 4. Here we have seen f of B is so 2 and 3. Okay, 2 and 3 means we are performing AND operation here. 2 and 3, they both gather at point 1. So we can say that these two are isomorphic lattices. We can means here given is the one example. We can go for this also. F of B and C, they come here also to D. Yes or no? F of B and f of C is we can take it as f of D also, because 2 and 3 both gather at 4 also. As they gather at 1, they gather at 4 also. So we can take as 2 and 3 as 4 also. Okay, so we can say that these two lattices are isomorphic lattices. Okay, it is the example of spatial lattices. Then it comes the distributive lattices. A lattice L is called distributive lattice if for any elements A, B, and C of L, it satisfies following distributive properties, which are A and B or C is equal to A and B or A and C, A or B and C is equal to A or B and A or C. These are the two properties that has to be possessed by the two lattices, then those will be known, that lattice will be known as distributive lattice. Okay. About this A, B, C are the elements of that lattice. Okay. If the lattice L does not satisfy the above properties, it is called non-distributive lattice. We'll see it with the help of example. The power set P of S of the set S under the operation of intersection and union is distributive function. Since A and B union C is equal to A and B union A and C, and also A union B and C is equal to A union B and A union C for any sets A, B, and C of P of S. Okay. This is also the task. If you go for take the set S, any set will be there. Suppose it is A, B, and C. Power set of that will be phi, set A, set B, set C, then set AB, set BC, set ABC, and set AC is remaining. Okay. Total 8 sets will be there in the power set. If we perform this operation between those power sets and the set S, we get it that the lattice is distributive lattice. Okay. So here we can consider it as the power set, and S is the power set of the set S is the distributive function. Okay. We can solve it with the help of truth table also, taking the intersection operation as AND operation and union operation as OR operation. With the truth table also we have already discussed it, and by taking the diagrams also in the unit sets, we have with the help of Venn diagrams also we have proved it. Okay, so that is known as distributive lattice. Now here, how the direct product of lattices, how does it, how will it be taken? We'll see that. Let L1 OR1 and 1. Okay, two lattices are there, L1 and L2. Two operations are given there, OR1 and 1, and for L2, OR2 and 2. These will be two lattices. Then L and R is the direct product of lattices where L is equal to L1 cross L2. Again, here cross means which term comes here? Can anybody tell me, please? Yes. Yes, can anybody tell me? Am I audible?
Yes, ma'am.
Yes, ma'am.
Cross is given there. Which term? Just now you have given the IC1. Have you heard about Cartesian product?
Yes, ma'am.
Then you should be able to tell this one, okay? In which the binary operations are and join and meet. Okay, these two operations will be can be considered, means or is also there, and it can be considered as join operation also. And if and is there, it can also be considered as meet operation. On L are such that for any A1, B1 and A2, B2 in L. Okay, the lattice elements are A1, A2, B1, B2. How the function pairs are given like A1, B1 and A2, B2. Okay, what is there in this one? A1, B1 or here we can say these terms also join. A1, B1 join A2, B2 is equal to A1 join 1, A2, B1 join 2, B2. Okay, see here how the operations are taken. A1, B1 join A2, B2. So A1 join 1, A2, and second element is B1 join 2, B2. Okay, here we have join 1 and meet 1, join 2 and meet 2. These operations are already defined. Similarly, if we consider A1, B1 meet A2, B2, what it will be? A1 meet 1, A2, and B1 meet 2, B2. Again, see here, A1 is joined with A2, B1 is joined with B2. Same here in the second scenario, meet operation is there. Meet operation between A1, A2 is the first element, and meet operation between B1 and B2 is the second element. Okay, this is the direct product of lattices. How is it taken? It is the definition of that. What the example given here is, consider a lattice L less than or equal to as shown in figure, where L is equal to 1, 2. Okay, L is 1 and 2. This is the lattice in the question which is given. 1 and 2, two elements are there. L is less than or equal to operation is there. What we have to do is here, we have to take the product of this 1, 2 with 1, 2. Okay, this L lattice is taking product with itself. So what it will come as L square, and operation is less than or equal to. It is as shown in figure. This is the answer figure. You can see. This is the question figure. 1 and 2. It is the lattice, and this is the answer figure. What is, which elements it will contain? 1, 1 will be there. 1, 2 will be there. 2, 1 will be there, and 2, 2 will be there. As 2 elements are there in the square, we will definitely have 4 elements, because 2 square is 4. Okay, so 1, 2, it is giving us, if we simply consider this set, 1, 2, Cartesian product 1, 2, which 4 elements will be there? 1, 1, 1, 2, 2, 1 and 2, 2. Like that, this lattice is formed. Getting? This is the direct product of lattices. Then the term comes the Boolean algebra. Okay, here we have completed the lattices. Then next we are considering the Boolean algebra. Now you might have gone through the digital techniques in your diploma. Okay, yes or no? You have idea about that?
Yes, ma'am.
Yes, ma'am.
Okay. In that also it is the basic Boolean algebra and operation or operation and all those things. Here also we are considering that Boolean algebra only, and some overview will be there, okay, for those concepts. A complemented distributive lattice is known as a Boolean algebra. Okay. Now, complemented distributive lattice. We already have seen the lattices. Then complemented means we are reverting the value. Complemented means again we will negation operation we know. Okay. So that negation operation comes here in the in picture for the Boolean algebra. Okay. So so the complement term comes. If A is there, then its complement is negation A or A complement. We say like that. And distributive lattice. We know distributive lattice. If distributive conditions are satisfied by the lattice, then it is known as the distributive lattice. It is known as the Boolean algebra. It is denoted by, how it is denoted? It is B. Okay. B here stands for Boolean algebra. Then AND operation is there. Okay. OR operation is there. Okay. Then complement is there. Okay. This small element here we can see that will be known as complement. And which values will be there? 0 and 1. Where B is a set on which two binary operations here and will be given by star and OR will be given by plus. Okay. These also we are familiar with. Star operation we consider it for AND operation or join operation. Again, same terms are there, only with if the algebraic system is different, then it is having the different name, but operation is one and same. Intersection is there, AND operation is there, join operation is there, that will be denoted by star. And if union is there, then OR operation is there, meet operation is there, it will be denoted by plus. Okay. Operation is same, but the nomenclature is different. Okay. And a unary operation, that is complement. Okay. It is unary. Complement is unary. Unary means what? We can take complement of one element also. So it is a unary. It's unary means one. If binary operations means what? We need two elements for that, A and B. Okay, if I have to perform A and B operation, then AND is the binary operation. Okay, because it requires two elements. That is not with the complement. We can take complement of one element. If A is there, its complement is A complement. We do not need any other element for that. So it is known as unary operation. Are defined. Here 0 and 1 are two distinct elements of B. 0 and 1 are two distinct elements of B. B is what? It is the Boolean algebra. Since B and OR is a complemented distributive lattice, therefore each element of B has a unique complement. Each element of B has a unique element. Which are two elements of B? 0 and 1. 0 complement is 1 and 1 complement is 0. Those are unique ones. Okay, 0 complement is 1, 1 complement is 0. That is unique one. So here it is given as each element of B has a unique complement. Then what are the properties of Boolean algebra? Properties of Boolean algebra. First one, it contains commutative properties. Commutative means we can change the place of elements. Means A plus B is equal to B plus A, and A star B is equal to B star A. What we can write it like. Then what is distributive? As we know, it is distributive lattice only. But one of the properties of this will be distributive properties. A plus B star C is equal to A plus B star A plus C, and second will be A star B plus C is equal to A star B plus A star C. This A is distributed with this star operation here, and here A is distributed with this plus operation. Okay, this is the distributive property. Then identity property, what it is? A plus 0 is equal to A. If A value is 0, 0 plus 0, it will be 1, means it will be A only. Sorry, 0 plus 0, it will be 0. And means ANDing operation we are taking here. And if A is 1, 1 plus 0, it is also 1. Okay. Then here is the ANDing operation of this one. This is the OR operation. Plus here is the OR operation. And star here is the AND operation. 0 and 1, it is going to give us 0. And 1 and 1, it is going to give us 1. So whatever the value of A will be, it is ANDing with 1, it will give us 1. And whatever the value of A will be, if it is ORed with 0, it will give us A. It is the identity. Then complemented law. What is the complementation? A plus A dash is equal to 1. What it is saying is A plus A dash. Now consider the value of A is 0. Okay, 0 plus A dash is 1. Okay, 0 plus 1, it is 0 or 1, it is giving us 1. Then suppose A value is 1, then 1 or 0, it is giving us 1. So the same case is here with the ANDing operation. A star A dash is equal to 0. Consider A value is 1, 1 and 0, it will give us 0. Same case will be there if A value is 0, 0 and 1, it is giving us 0. So it is a complemented law also. Then subalgebra is there. It is the next part of the Boolean algebra. Consider a Boolean algebra B star plus complement 0 and 1. Star here again is referring to ANDing operation, and plus here is referring to OR operation. And let A is subset of B. Then A star plus complement 0, 1 is called a subalgebra or sub-Boolean algebra of B if A itself is a Boolean algebra. Okay, A is subset of B when A is also Boolean algebra. And B is Boolean algebra, that we know. But if A is to be Boolean algebra of B, then itself has to be the Boolean algebra. That is, A contains the elements 0 and 1 and is closed under the operations star, plus and complement. Okay. Example, consider here the Boolean algebra D70 whose hash diagram is given in the figure. Here we can see 70. What are the elements that divides the 70? 1, 2, 5, 7, 10, 14, 35 and 70. Here we can go for 1, 2 means 70. All these upper elements are can be divided by 1 also. Means 2, 5, 7, 35, 14, 10, 70. Okay, so 1 is the base for this. Then if we consider these 3 elements, 2, 5 and 7. 2 and 5 we can go for 10. 5 and 7 we can go for 35. 2 and 7 we can go for 14. Yes or no? And all of these are again we can go for this 70. Okay. 70 is divided by 35, 70 is divided by 14, 70 is divided by 10. Okay, like this is the hash diagram given for this example. clearly A is equal to 1, 7, 10, 70. Okay, it is whole Boolean algebra. Okay, what we can take here is A is 1, 7, 10 and 70, and B is equal to 1, 2, 35, 70. 1, 2, 35, 70 is a subalgebra of D70. D70 is containing all these elements. Okay, and 1 is the lower bound, 70 is the upper bound, and we can say that containing these elements, elements of these elements, elements of these lattice, any elements will be there. We can say that these will be the subalgebra. Okay, we can take 1, 7, 35, 70 also. We can take 1, 2, 14, 70 also. 1, 5, 10, 70 also. Like that, since both A and B are closed under operation and, or, and complement, we can say that it is the A is the, or D, A and B are the subalgebras of D70. Okay, this is suppose the D70 hash diagram, and A and B are the subalgebras of that. Okay, we can take any combinations in between. Just we have to keep 1 and 70 constant. Means 1 is the lower bound and 70 is the upper bound. Between these two elements we can change. Okay, and we can take multiple elements also, not only 2. We can take 1, 2, 10, 14, 70 also. 1, 2, 35, 70 also. 1, 2, 5, 7, 70. Like this, we can take any elements in between 1 and 70 to consider the subalgebras. Okay. Then here comes the isomorphic Boolean algebras. Okay. Again, the same concept that we have seen in lattices that we are going to apply here. Isomorphic Boolean algebras. Two Boolean algebras B and B1 are called isomorphic if there is a one-to-one correspondence. F is the function from B to B1 which preserves the three operations plus star and complement for any element A, B in B. Okay, here we can again consider these operations. F of A plus B is equal to F of A plus F of B. F of A star B is equal to F of A star F of B, and F of A dash is equal to F of A and complement of that function. Here only complement of that element is given. Here complement of function is taken. Okay. What example is taken here? The following are two distinct Boolean algebras with two elements which are isomorphic. Okay. Sorry, I'm not feeling well today that much. Okay. The first one is a Boolean algebra that is derived from a power set P of S under set inclusion. Okay, set inclusion again, which is a subset concept comes here. That is, let S is equal to A and B is equal to P of S union, intersection and complement is a Boolean algebra with two elements. P of S is equal to phi and A. If S is A, okay, then what will be its power set? S is the set containing only one element, that is A. So what the power set of A will be? It is phi and set A. Okay. Then what we can say is B is P of S. Means again this one phi and A, and under the operations union, intersection, and these complement. Okay. It is also the Boolean algebra. Okay. In which P of S is these two elements. Okay, because S given here is only A. Only one element is there. The second one is a Boolean algebra, B, or, and complement with two elements 1 and P. Here P is a prime number. Okay, second example is here. P is what? It is a prime number. Under the operation divide. Okay, under the operation divide. Let B is equal to 1 and P. 1 and P. So we have 1 and P is equal to 1. Here P is the prime number. Okay. What the prime numbers are there? 2, 3, 5, 7, 11. Okay. Means prime numbers are what? They are only divisible by 1. Not other any element can be can divide that prime number. Okay, this is the definition of prime number. B is equal to 1. P is the set. P is any prime number. 1 and P is giving us 1. Okay, and 1 or P is giving us P. Also, 1 dash is equal to P and P dash is equal to 1. It is given the Boolean algebra example here in this second example. P is the prime number. Means the highest element is P and lowest element is 1. Here it is the Boolean algebra. 1 is the least element, P is the greater element. If we take AND operation between these two elements, 1 and P, it will give us 1. Okay, means what? It is a join of these two, and 1 or P, it will give us meet, that is P. Okay, P is the greatest element. Okay, so this condition gets satisfied, and complement also we can give as 1 dash is equal to P and P dash is equal to 1. Okay, so this one also is the example of isomorphic Boolean algebra. Okay. Then these are some properties of Boolean algebra. In this it comes, the table shows all the basic properties of a Boolean algebra, B, star, plus, complement, 0 and 1. For any elements A, B, C belongs to B. The greatest and least elements of B are denoted by 1 and 0 respectively. Okay, 1 is the greatest element and 0 is the least element. Then all these properties are defined here. We already have gone through, just I will explain little bit. A is less than or equal to B if and only if A plus B is equal to B. Plus here is again which operation? OR operation or meet operation. Okay. Second law, what it is? A is less than or equal to B if and only if A star B is equal to A. Star here again it denotes the AND operation or join operation. Okay, these are the properties of Boolean algebra. Then idempotent law, again A or A is equal to A and A is equal to A. This is known as idempotent law. Then we can also solve it with the help of truth tables. The easiest way to go for, we can what we can say, prove all these properties. Okay, and already we have done tons of times before this. Commutative property is there. Then commutative means change of element. A plus B is equal to B plus A star B is equal to B star A. Then associativity again, it's for A plus B plus C is equal to A plus B plus C. Means here first B plus C is performed, then it is ORed with A, and same will be the result for first A plus B will be performed, and then it will be ORed with C. Same is case with the star operation also. A star C star C is equal to A star B star C. Okay. Then absorption law is there. How it is absorbed? A plus A star B is equal to A. B will be absorbed here. So the name is absorption. Same, A star A plus B giving us A. B will be absorbed. Then identity laws. What are those? A plus 0 is giving us A, and A star 1 is giving us A. These are known as identity laws. The null laws, what it is? It is A star 0 is equal to 0 and A plus 1 is equal to 1. Then distributive laws, what is distribution? A star B plus C, A star B plus A star C. The star operation is distributed on B plus C, B and C. Same here, A plus B star C is equal to A plus B star A plus C. This plus operation is distributed on B and C. Then complement laws are there. 0 complement is 1, 1 complement is 0. A plus A dash, that is A plus A complement is 1, and A star A complement is 0. Then involution law. What is involution law? A complement and its complement is giving us A. It's having one more name. Okay. You have to think on this. What is the second name for this? Complement of a number is giving us that number. Okay. It is one more property of Boolean algebra. And what the De Morgan's laws are there? A star B. Excuse me. A star B dash is equal to A dash plus B dash. And the second one is A plus B dash is equal to A dash star B dash. Okay. These are the De Morgan's laws and properties of Boolean algebra. Then it is the last part of the chapter, Boolean functions. Okay. What the Boolean functions are? A Boolean function is a special kind of mathematical function f from x raised to n to x. It is of degree n, where x is equal to 0 and 1. It is a Boolean domain and n is the non-negative integer. Non-negative integer, again, it starts from 1 to goes up to infinity. It describes the way how to derive Boolean output from Boolean inputs. Like example given here is f is equal to ab, it is equal to a dash b dash. How the function is defined here is a dash b dash. This is a function of degree 2 from the set of ordered pairs of Boolean variables to the set 0, 1. Here how it is given, x is 0 and 1. It is, and function is from x raised to n to x. And what the example given here is f of ab is a dash b dash. This is a function of degree 2 from the set of ordered pairs of Boolean variables to the set 0 and 1, where how it is given, f of 0, 0 is 1, f of 0, 1 is 0, f of 1, 0 is 0, and f of 1, 1 is 0. Consider here a and b are the two elements, and take the combinations of a and b with 0 and 1. F of a and b means f of 0 and 1. What it will be? 0 complement, 1 complement, means 1 is 1 star 0 again. Okay. And 1 star 0, what we get is 1 here. Okay. This Boolean we will see with the help of whiteboard. suppose here f of a comma b is equal to a dash b dash. Okay. Okay. And what the elements given are 0, 1. Okay. Then if I have to consider values of a and b with all the combinations, then what I will do is f of a comma b is equal to f of 0, 1 is equal to 0 dash 1 dash. In between, this is the star operation. Okay, star operation is not given there, means it is the hidden one. Compulsory here we have to take the star operation. Means what it will be? 1, 0 complement is 1 and 1 complement is 0. And 1 star 0, it is equal to 0. Is it the one? Are you getting it? Then suppose I take f of a comma a. It is equal to f of 0, 0. It is equal to, by our definition, 0 complement star 0 complement. It is equal to 1 star 1 and it is equal to 1. Same case with f of b comma b. Boolean algebra is what? We are taking combinations of elements whichever are possible. Okay. So b is 1 here. So f of 1 comma 1. It will be equal to 1 dash star 1 dash. It is equal to 0 star 0. It will be equal to 0. And last combination we will take is f of b comma a. What it will be? Equal to f of 1 comma 0. It is equal to 1 dash star 0 dash. It is again equal to 1 dash, that is 1 complement is 0 star 0 complement is 1. It is also equal to 0. Okay. So what we get it like this. Okay. What our operation is a dash b dash. And if we perform all these values, then we get this one. Okay. So this is just example of Boolean algebra that we have seen. Here our syllabus ends. If you have any type of doubt, you can clear it coming to me, or you can text me, or you can call me. I will be there for you to clear the doubts, and all the materials with MCQs and notes, those will be in your teaching diary. Probably tomorrow, if not possible today, I will give it, or I think I already have given it in your teaching diary. You just go for that. And that's it. Any doubts are there for today's lecture? Yes. How the DMS subject is that you feel? Is it easy or is it difficult?
Easy.
So,
Yes, it's easy one. For last some chapters, we might face some difficulties. So for clearing the doubts, you can come to me. Okay. So that's about the DMS subject. Okay, then just give the attendance. Yes.
Ma'am, from exam point of view, which MCQ we have to practice?
If you practice, means you go for theory first, then you will get all the minor points in the theory, and from which you can go for the MCQs. Okay, you can go for any type of MCQs. Again, if possible for me, I will also give you MCQs. Okay, if
Yes, ma'am.
again, okay, huh.
Last year's question paper, if
No,
we get,
no,
it
no.
will be very helpful for us.
I think we cannot get it, means last year question paper. I think because it was with the help of that software, university software. Though I will ask in the department. Okay, if I get it,
Yes,
then
ma'am. If we get
oh.
that MCQs which were appeared in the last exam,
Yes,
we'll
yes,
get some idea.
Okay, not an issue. Which are the absent numbers today? 1 is there, 2 is there, 3, 4, 5 is not there, 7 is not there, 9, 14, 5, 7, 9, 14. Okay, then you all can leave the meeting. Here are syllabus ends. Okay. Have a good practice of the example. It will be easy for you. Okay, I'll end the meeting.
Okay.